So you can make beyond new states, depending on chemical stability, you can make beyond new states shorter, but you can't make them longer. So even if you find that your drug is stable for 2 years against hydrolysis, you're only looking at chemical stability. So these beyond new states are taking into account a lot of the other types of stability, so mostly microbial growth, physical stability, things like that. That's what assigns that short 14 days. And if you're just looking at chemical stability, you can't make the beyond new state any longer than 14 days. So in class we went through a couple examples. So if you have a drug that degrades by hydrolysis and you know the rate constant of that, you can calculate the shelf life, right? You're just using the T90 equals 0.105 divided by the rate constant, and you can get a very long shelf life, but you would still assign that a beyond new state of 14 days, even if you get a super long shelf life from chemical degradation. However, on the other hand, if you find that you have a something that degrades even, sorry, this should be if you find something that will hydrolyze faster and you get a shelf life of less than 14 days, then you would assign it a shorter beyond new state. Does that make sense? So finally, the last lecture, which is most of the new calculations, are looking at buffer solutions. So remember, for buffer solutions, our main components are a weak acid and a conjugate base. So any buffer is going to contain those two things. Your weak acid and your conjugate base dissolved in water. And the important characteristics of buffer solutions are the pH. So this is whatever pH you formulate your buffer at, and its buffer capacity. And remember, the buffer capacity is a measure of how well the buffer is going to maintain that pH that you made it at. So how close will it keep your pH there? So for this example, what is the pH of a solution with these components? So when you're looking at questions like this, what you would need to look at first are figure out which component is your weak acid and which one is your conjugate base. So for this example, we have sodium phosphate. These are our two buffer components. We have sodium phosphate and disodium phosphate. So in this example, sodium phosphate is our weak acid, and disodium phosphate is our conjugate base. Just remember, the conjugate base is when you have the reaction for acids and bases. The HA form is your weak acid, and then the A- form is your conjugate base. So if you have sodium phosphate is NaH2PO4, and you'll have a table showing all of these too. And disodium phosphate is Na2HPO4. So if you take away the sodium, that means you have H2PO4 minus plus water will give you HPO4 2 minus plus H3O. So the one that's more negative is your conjugate acid, or your conjugate base. So that's this one. And this is your weak those numbers in to understand the lab. So your pKa is given, right? 7.21 plus log of 0.02 over 0.1. Okay, so that is 7.21 minus 0.70, which is the pH is 6.5. So that would be B. Okay. So the other calculation for buffers then is also to figure out what is the buffer capacity of your solution. So to calculate buffer capacity, so these are the same numbers that we had in our first example, 1.2 grams of sodium phosphate and 0.3 grams of disodium phosphate. So we've already calculated the molar amounts of those, right? So remember our HA was, what was it? 0.1 molar, and A minus was 0.02 molar. And then we use the Van Slyke equation. So remember the Van Slyke equation is beta, which is the buffer capacity. So that's what you're solving for, is equal to 2.303 times C times Ka times H3O squared. So the numbers that you need are C, right? And then remember, C is the concentration of your weak acid and conjugate base added together. So in this example, C is 0.12 molar, right? Ka, remember that your pKa is your minus log of Ka. So you would take the anti-log of your pKa to get the Ka. So anti-log of minus 7.21 to give you your Ka value. And then remember that pH is equal to minus log of the H3O concentration. So you would do the anti-log of our pH that we found in the previous problem, which was 6.5. So then you would plug all of these numbers then into the Van Slyke equation to get the answer. So that's buffer capacity. So this one is D. So in both of these examples, the amounts of the two components are given, the sodium phosphate and disodium phosphate. So sometimes it can also be the opposite, right? You can have to figure out what those amounts are for the given buffer capacity and pH. So these are the same equations, but you're just solving for something different. So in this example, you would need to first figure out your ratio of the weak acid and conjugate base, and then we would use the Van Slyke equation to solve for the buffer capacity. So why don't we take a break and